Hey, welcome back to your favorite pre-calc class. We take a look at our U-shaped graphs, our quadratic functions. These are called parabolas. And our vertex form, which is a very useful form for a quadratic, is this a times the quantity x minus h squared plus k. So this vertex right here, the bottom of the graph, or let me put it in red right here, that HK, that minimum point right there on that U-shaped graph, that's going to be our HK. So we want to have, in vertex form, we want to have numbers, a point for that HK, and then we want to also have a number for the A, this number in front. If the A is positive, this graph is going to open up, like something like this, right? If the A is negative, it's going to open down. Maybe something like this instead. Right? Flip that U shape over. Right? Our vertex again is the HK. That's our vertex. Okay. The standard form, I'll give you this. The standard form of a quadratic, is not as useful, but it's quadratic degree 2, ax squared plus bx plus c, right? That's our standard form, polynomial form there. Well, we're given an equation here, y equals negative 2 x plus 3 quantity squared. Let me go ahead and write vertex form right above it. Let's see if we can identify, graph this thing. Okay, first of all, our HK. H is after the minus. Maybe you want to write it this way. X minus a negative 3. Minus a negative 3 is the same as plus 3. So the H would be that negative 3. And then the K is that positive 8. So negative 3, 8. I'm going to put that point on there. Now notice the A in front, that negative 2 right there that I circled in green. It's gonna have this thing will flip that over. All right, so it's gonna open down, just so we have an idea. But let's go ahead and find our axis of symmetry. Now I haven't actually talked about the axis of symmetry yet, so let me come back up here. Our axis of symmetry is the line that goes right through the vertex. The equation of that is x equaling h here, okay, when it's in vertex form. But it's the line, the imaginary line that goes through the vertex about which it's reflective, right? So in other words, if I have this point, it's a distance of 2 this way, at the same height, it'll also be a distance of 2 away from it on that side, right? So it's kind of a axis of symmetry. It's symmetrical about that line. Right? That's what I'm trying to say. It's symmetrical about that line. So what's our axis of symmetry here? Well, it'd be x equaling h. Our h here is negative 3. So I'm going to go ahead and put that imaginary axis of symmetry on there. I know it's going to be reflective about that line. And then what I like to do when I'm graphing this is, as soon as I have my vertex, negative 3, 8, I always like to pick a couple points, and I'm going to label this. And remember, the axis of symmetry goes right through that middle of that, right? It goes right through that vertex. So pick a couple points to the left of that x value. Pick a couple points to the right of that x value. And then you can plug them in one by one and get some other another look at this. So let's plug in negative 4. Negative 4 plus 3 squared plus 8. So I get negative 2, negative 1 squared is just a positive 1. So I got negative 2 times 1 is negative 2 plus 8, so I got 6. So I negative 4 comma 6. I could throw in negative 5. And negative 5 would give us negative 2 squared is a positive 4. So negative 8 plus 8 is 0. I could plug in negative 2, and guess what? I'd get 6. I could throw in negative 1, and guess what? I would get 0. And graph those points. See how that's reflective. And then we could kind of draw our U shape. Oh, that's pretty bad, but whatever. Anyways, that thing's kind of upside down. U. All right. Now, if I was going straight to just finding the x-intercept by letting y be 0, I could do that. If y is 0, let's replace y with 0 and solve for x now. Let's find where this x-intercepts are. And I know you probably already see them on the graph. That's okay. We'll do it algebraically as if we didn't know. I'm going to divide both sides by -2. So I got x plus 3 squared equals 4. I've got a perfect square, so I'm going to go ahead and square root both sides. So I got plus or minus 2. Now I'm going to subtract 3. So my x-intercepts are -3 plus or minus 2. Well, -3 plus 2 is -1. Here's one of my x-intercepts. The other one is -3 minus 2. There's my other x-intercept, the -5, 0. We already knew that. We got lucky because we plugged in those points already. But that's how algebraically how you find those. Let's go ahead and find the y-intercept. That one we do not know. We do know it's going to keep going down and eventually cross it, right, the y-axis. But let's go ahead and let x be 0. So I let x be 0. 3 squared, 9. So I get -18 plus 8, so -10. So 0, -10 is about right here. So it's going to eventually hit that right down here. It's going to extend down and finally cross at -10 down there. So there's our our y-intercept. So instead of vertex form, what if we were given this in standard form, ax squared plus bx plus c? Well, if you were to actually complete the square, so you take an a out, push that plus c out, blah, 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 blah. Anyways, you complete this square, you guys. What you're going to get is x plus b over 2a 20 squared plus blah, 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 blah. The point in doing this, completing the square, is to recognize that that's your h right there. So if you're in this form, if you're already in this ax squared plus bx plus c form, the standard form, then your axis of symmetry, instead of going to the effort to complete the square, just know that your axis of symmetry is -b over 2a. So you've got, this is 3x squared plus 6x plus 1. So your a is 3, b is 6, c is 1. So let's find the middle of this graph. -b over 2 times a. So x -6 over 6, -1. So x would be -1. That would be the middle of the graph. And so and if you wanted to, you could even find the vertex from there by plugging it in. Let me erase this real quick. We know that's our axis of symmetry. So the vertex has that -1 value. Let's find the y value. So we got 3 minus 6 plus 1. I got -3 plus 1. I got -2. Okay, so there's our vertex, -1, -2. And same thing for this a value. If it's positive, notice it's a +3, it's going to open up. So I know we didn't graph it, but I do know it's going to look something like that, right? The question didn't ask us to graph. If I was graphing, I would start at this vertex, -1, -2. That's my vertex, right? I would go to the left a couple, and I'd go to the right a couple, and I'd just plot the points. I'd be a little more accurate with it. But all right, let's move to this next one. So now we got negative 2x squared minus 5x plus 1. Find the axis of symmetry. This would be a good little you try problem if you want to pause the video. So if you want to go ahead and check yourself at negative 5/4, what should end up being, so negative 1 1/4. This would be your axis of symmetry, negative 5/4. So that's the middle of your parabola. I don't know where the vertex is unless I plug it in, so I'd go ahead and plug it in for x. Negative 5/4 squared minus 5 is negative 5/4 plus 1. Let's see, that would give us negative 25 over 8 plus 50 over 8 plus 8 over 8. So 25 plus 33 over 8, looks like. So 33 over 8. So our vertex is at negative 5/4, and I'm up like 4 1/8. So about right here. Notice my A value is negative, so I know it's going to go upside, flips that U over, or something like that, if you're actually drawing it. But again, we just want the vertex and our axis of symmetry, and that line down the middle of that thing. Well, with these parabolas, depending on if it's flipped over or not, that'll tell us whether we have a maximum value, right? So the vertex is where we're going to have a max. If it's U-shaped, then it would be a minimum, right? Like that initial picture, that would be the absolute minimum. Flipped over, we have absolute maximum. So this says, determine without graphing whether the quadratic function negative 2x squared plus 8x plus 3, does it have a max or min? So hopefully you're looking at that A right there and know, well, it's negative. So wherever it's at, I know it's flipped over. So I'm going to have a maximum right there. I'm going to have a maximum value. And then what is the value? Well, it occurs at the vertex, right? So in order to find the vertex, I say, well, it's on the axis of symmetry. So let's start out by finding our axis of symmetry for this negative 2x squared plus 8x plus 3. So since it's in standard form, go ahead and plug it into negative b over 2a. And it looks like we get, negative 8 over negative 4 is positive 2. So the x value of the vertex is a positive 2. Let's find the y value. So we got negative 2 times 4, I get negative 8. Plus 16 plus 3, so I get 8 plus 3, I get 8 plus 3, sorry, is 11. So 2 comma 11, there's our vertex. Okay, it says find the value then. So what is the max? Max is 11. It occurs at x value of 2. And so that would be the point 211. So I obviously did not draw this to scale. But there's our max. Now the domain and range. The domain of a quadratic, you notice you could plug in any x value you want. So if you're looking left or right, there's no breaks in this. So your domain is going to be all real numbers. Your range, on the other hand, this is going to come up to whatever y value is since it's flipped over, right? So the range would be coming from negative infinity up until that maximum of 11, and it just hits that 11 and stops. So the range depends on where that vertex is and if it's U-shaped or flipped over. All right, let's take a look at this one here. We got x squared minus 6x plus 5. The vertex would be on the axis of symmetry. So notice it's given in this standard form. X squared plus bx plus c. We've got x squared minus 6x plus 5. So let's find the axis of symmetry. Negative b over 2a. So negative, our b here is negative 6 over 2 times a. So our axis of symmetry is 6 over 2, which is 3. 1, 2, 3. So we know the vertex is on that imaginary line. So the vertex is 3 something. Let's plug it into the equation. Find the y value. We got 9 minus 18 is negative 9 plus 5 is negative 4. So I got 3. Negative 4 is our vertex. Now, I like to, once I have my vertex, just go to the left a couple and to the right a couple. That's kind of my preference. But we'll go ahead and we'll jump into our x-intercept and y-intercept. We just want to have a couple other points here to give us some shape to this quadratic. So let's find our x-intercept by letting y be 0. If y is 0, let's see if this is this factor. It does factor. So it looks like we have 1 and 5 are our x-intercepts. 1 and 5 is where y is 0. So 1, 0, 5, 0. All right, we could draw it because we've got points equidistant both sides there of the vertex. Well, let's go ahead and find our y-intercept by letting x be 0. So now let x be 0. So we have 0 minus 0 plus 5. 5, 1, 2, 3, 4, 5. Didn't draw that very good, but it's going to go through that 0, 5 right there. There's our y-intercept. There's another point on that graph. And maybe you want to make this one a u-try problem. Y equals x squared minus 5. Notice that there's no bx term there, so what would your b be? All right, why don't you go ahead and check your axis of symmetry work there. You should have x equaling 0 for the axis of symmetry, which is the input for your vertex. So they put 0 in for x, and then you get 0 squared minus 5, negative 5. So you know there is your vertex. The a value is 1, right? It's a 1x squared minus 5. So it's going to open up. You know this thing's going to open up. But let's go ahead and find our x-intercepts. Y equals x squared minus 5. Let y be 0, x squared minus 5. Let's add 5 to both sides. Square root, square root. So we get plus or minus the square root of 5. There's our x-intercepts. Plus or minus the square root of 5 are our x-intercepts. So that's like 2 point something, 2 point something, negative 2 point something. So it's going to hit those two spots on the x-axis. If you let x be 0 now, we already had this. We knew it was crossing because the vertex is right on that y-intercept, isn't it? Notice here that we have a domain, all real numbers. Doesn't matter what our x is, it'll spit out a y. So our domain, all real numbers. Range, on the other hand, notice our lowest y value here is at negative 5, and then it goes up to infinity, right? So our range here would hit that negative 5 and then go up from there. When we make this next one a u-try problem, go ahead and pause the video. Make sure you put it in standard form first, ax squared plus bx plus c before you start it. So find your axis of symmetry, then your vertex, and so on. All right, should have had your axis of symmetry there, x being 2. I did that first, and then I found my vertex from that input point, right? Which spits out a y value of 2, so 2, 2. And then notice the a value here is 1, right? So it's going to open up for us. But let's go ahead and algebraically find your x-intercept by letting y be 0. Notice this doesn't factor. Let's go ahead and just plug it into the quadratic formula. X equals negative b plus or minus square root of b squared minus 4ac all over 2a. So we get 4 plus or minus the square root of 16 minus 24 all over 2. So we get x equaling 4 plus minus the square root of negative 8 all over 2. So we get 4 plus or minus the square root of negative 1 times 4 times 2. I 2. So 4 plus minus 2i root 2 all over 2. Both those go into 2. So it's 2 plus or minus I root 2. Well, this is a real number graph, right? So this is saying these are complex zeros. They're not going to show up on a graph. In other words, there's no x-intercepts. Well, why is there no x-intercepts? Well, we know this thing opens up, right? It's going to open up. It's not going to cross that x-axis. That's why you got those imaginary roots or imaginary zeros there. So let's go ahead and move into our, y-intercept. 0 squared minus 4 times 0 plus 6. So when x is 0, y is 6. Let's put that on the graph. Right there. X is 0, y is 6, which is 2 units away. So I know, if the middle of my graph here, this vertex, is at 2, if I went to the left a couple, and the right a couple, right? We just plugged in the 0, it spit out 6. So if I go to the right, well, it should be 4 right there. If I plug 4 in, it'll also spit out 6. Right, because it's symmetric. All right, it's 2 units from that line of symmetry on both sides. All right, but you can plug in some other points if you want to check that and make sure you got an accurate parabola there. Our domain, as always for these quadratics, is going to be all reals. Our range, on the other hand, notice it's got a lowest value of 2, y value, and it just keeps going up. Right, so our range would be from 2 on up on this. We do some modeling with these quadratics, and in these application problems, we're going to be like maximizing or minimizing, finding max heights or whatever. And so we're going to be looking for the vertex, right? Because if we've got a model that's like this, we're going to have a minimum value. If we've got a flipped over parabola, we're going to have a maximum value. And so we're always going to be looking for that vertex. That's kind of going to be the key for this. So here's this first one. Suppose you got the height of an object here, h of t, 512t minus 16t squared. Let me write it this way. Negative 16t squared, put in standard form here, plus 512t. And so if I was graphing that, something like this type of deal, right? We're not going to worry about the graph. I'm just trying to give you a visual. Where h is measured as the height, and this is time t in seconds. Find the maximum height and the time at which the object hits the ground. Well, we know the maximum height would be right there, right? And so the maximum height occurs where? On the axis of symmetry. Right? It's going to occur on an axis of symmetry. So number 1, max height is on axis symmetry. So x equals, in this case it's t. T equals negative b over 2a. So our t equals negative b. Right, at squared plus bt plus c. Right, so our b here is 512 over 2 times a. So negative 512 and negative 32 ends up being 16. So I didn't draw this. Let me make this a little bit more accurate picture here. There's our max height right there, right? We know it's going to occur at a t value of 16. It's right on that axis of symmetry, right? Well, it says Find the maximum height. Well, it happens at 16 seconds. What is it though? Well, we better plug it in and find out what it is. Max height, t being 16. So h of t, h is 16, negative 16 times 16 squared plus 5, 12 times 16. And that ends up being 4,096. So that's the max height, 16 comma 4,096 feet. That's your time, seconds, that's your height in feet. So 4,096 is maximum height. Now, when does it hit the ground? Notice, when does it hit the ground? So we're really solving. When's our height 0, right? So let's take a negative 16t out of both of these. Add 32 to both sides. Divide by 16 both sides. So we know at 0 seconds and at 32 seconds it's going to hit, right? So the projectile is like it's shot up or whatever happens. It hits its maximum height up here, falls back down, and hits the ground again, right, at 32 seconds later after it was shot up. All right, let's do this next one here. We got daily revenue R achieved by selling X boxes of candy. So they give you the revenue function and the cost of selling X boxes. How many boxes must be sold to maximize profit? Well, your profit would be revenue, however much money you bring in minus your cost or your expenses, right? So as a function, your profit would be the revenue minus the cost. That's what we're trying to maximize this profit, right? So if this profit's going to be maximized, if we're going to have a maximum, it's going to be something like this, right? It's going to be a flipped over U. We're going to have a maximum. So we're looking for like how many X boxes are we going to sell to maximize this profit. That's what we're looking for. Let's find our profit function first. Well, our revenue is given right there, 9.5x minus 0.04x squared, minus our cost, our expenses. Let's go ahead and distribute that. Again, notice this A value is negative. So we do know it's flipped over, right? But this is our profit function. I'm trying to maximize this. So this is like the ax squared plus bx plus c. So we're like, well, it's going to maximize that at our vertex. The vertex is on this axis of symmetry. So let's find this axis of symmetry, x equaling negative b over 2a. So we had negative 8.25 is our b over 2 times negative 0.04. And so our x ends up being 103.125. This is boxes, so we'll just round to the nearest box. 103 boxes. So we want to sell 103 boxes to maximize our profit. Now, what would the maximum profit be? Step 1, step 2, what is the max profit? Well, we know it occurs there. In other words, where's our vertex at, right? What's the y value there? Let's throw it into our profit function. And this will end up being $175.39. All right, this next one we've got, it says among all pairs of numbers whose difference is 24. Okay, so we got a pair of numbers, their difference is 24. Let's say it's x and y. Well, one equation would be their difference subtraction is 24. Find a pair whose product is as small as possible. We're trying to minimize this product, right? So the second equation might be their product x times y. We're trying to minimize this. Trying to minimize that, right? The product x times y. Trying to minimize that. So I would take a look at that first function. I say, you know what? I can solve that for x. You know, if their difference x minus y is 24, let me solve for x and then plug it into the other equation. So let me throw that in. X equals y plus 24. If that's what x is, now let me distribute that. Y squared plus 24y. So notice now we're down to one variable, just y's, right? I mean, normally we have x's, but it doesn't matter. We just got y's. It's a quadratic. Y squared is going to open up, right? Something like this. All right, y is the input, p is the output. We're trying to minimize this, so we're just looking for where this is, right? Where's that at? Well, I know normally it's ax squared plus bx plus c, but again, that's just in terms of y's. We're just trying to minimize it. Find the axis of symmetry. Normally it's x equaling negative b over 2a. Today, or on this one, it's y equals negative b over 2 times a. So it'd be at a y value, when y is negative 12, it will minimize that. So we know y is negative 12. We also know their difference is 24. So x minus a negative 12 equals 24. So x plus 12 equals 24. If I subtract 12 on both sides, then x actually has to be 12 as well. That's our pair of numbers, 12 and negative 12. And notice if we multiply those two together, right, what is the minimum product? What is the minimum product? So step 5. If x is 12, y is negative 12, minimizes it. What is that minimum? Negative 144. That's the minimum product you'd have based on the restriction that their difference be 24. All right, suppose you have 900 feet of fencing. You want to enclose a rectangular field that borders a river. Let's draw. Here's my little river, and I want to fence it in, right? So I don't need to fence the river. I have 900 feet of fencing. Let's call this x, and y. So this perimeter of the fencing, x plus x, 2x plus y, right? And I have how much of this fencing? Well, I have 900 feet of perimeter, right? For these three sides. What we're trying to do is we're trying to maximize the area, right? How much area is this? Well, we know area of a rectangle's length times width, right? So we got x times y here. That's what we're trying to maximize. We're trying to maximize the area. All right, so we need to create a quadratic. So what I'll do is, similar to this last one, I'm going to go ahead and solve for one of the variables on this first equation. So y equals 900 minus 2x, and then I'm going to throw that in over here. So I have a equals x times the 900 minus 2x for y. And notice when I distribute that, 900x minus 2x squared. That's what we're trying to minimize, right? So if you had a visual of this, right, we're like, hey, what's the x that will maximize this area quadratic? But we have because we have a model for this now, right? A quadratic model for this. So we just say, well, it's going to happen on that axis of symmetry. X equals negative b over 2 times a. So you got negative 900 over negative 4 is 225. So we want to have 225 feet of fence, or 225 for the x of that fencing. And remember, the perimeter is, we had 900 equals 2x plus y. So 900 equals 2 times the 225. Let's find what the y has to be. Subtract 450 from both sides. So it looks like the y's got to end up being 450. So we want to have the dimensions of this to be 225 by 450 feet. And the largest area that can be enclosed then, what is this area? X times y, 225 times 450 is 101,250 square feet is how much area we can maximize with 900 feet of fencing along this river. All right, our last one here is, can you go backwards? Can I take a graph and write the equation for it? So the first thing I'm looking at is, hey, I've got this axis of symmetry. Vertex is right there. It looks like that vertex, HK, is at negative 1, 3. There's my HK. Remember, if I'm writing the equation in vertex form, I got to have an HK, and I got to have a value for A as well, right? And I know it opens up, so I know A is going to be positive on this. But the question is, what value is it? I really don't know the value of it yet. So I'm going to have to solve for A. So what do we have? Well, we have HK. We also have some other points, like this one right here. See that 0, 5? That's just some random xy that's on the parabola. So I'm going to go ahead and use one of these points. And let's plug it in to our vertex form and solve for A. So y would be 5, A we don't know, x would be 0, h would be negative 1, k would be 3. 0 plus 1 is 1, squared plus 3. 5 equals 1a plus 3, subtract 3. Hey, there's our A. A is 2. So now we know our vertex, negative 1, 3. There's our HK. Our A is 2. Let's write the equation. So we got 2x plus 1 squared plus 3. There's the vertex form. Now, if they actually asked you to put it in the standard form, you could just multiply that x plus 1 squared out, right? Distribute or FOIL that thing. Get x squared plus x plus x. You got 2x plus 1 plus 3. Then distribute that. Combine like terms right there. And there it is in standard form. If you want to put it in standard form, you could do that as well. Thanks so much for taking notes on quadratics. See you next time.